Thank you. Thank you, thank you, thank you. All right, well, we'll see what happens, but anyway, I think it's good for you guys to have some, time pressure questions before the test, and so I think we've achieved that today, if nothing else. I hope you guys did okay. I'll find out. But obviously, I don't expect everybody to get everything, right? But if you made significant progress towards 3 of them, then you probably have more than 100%. So anyway, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for the break. And just ask you to guide our steps today, Lord. Help us to glorify you what we do. In your name I pray, Lord Jesus. Amen. Okay, so I want to talk about this result that I projected last time. I'm not going to prove the whole thing. I want to talk a little bit about some of the some of what's involved in proving it. First of all, the claim. So, let's talk a little bit more about this. What does this mean? This is by definition, x, t of x, t squared of x, and so forth and so on, right? And so this is the so-called T-cyclic subspace generated by, by x, which is in V. And here, what are we assuming? We're assuming T is a linear transformation from V to V, right? So that's the context here. And this is part of what is really part of the bedrock on which the Jordan form is built. So it's important for us to understand a little bit more about it. As I told you, I won't prove everything, but I want to say a little bit more about this. So first of all, you can argue, and I won't do this, but you can prove, that probably would make a decent test question, wouldn't it? That this is a subspace of V, all right? So if you were to, you could prove it satisfies the subspace test, all right? Zeros in there, and so forth. So it is a subspace, and it's also it's a T invariant subspace, right? So we also have this, T of this is a subset of that, all right? So it is in fact a T invariant subspace. And I think we can even argue that it's the, I want to say it's the smallest T invariant subspace, which includes X. So if you have a T invariant subspace which has X in it, then this is the, the smallest such subspace. So to see that this forms a basis, that's actually kind of an interesting little argument. So obviously, this assumes, I think I've buried, we're assuming, for x not equal to 0, I think. Because if x is 0, then that's not a basis, right? It's not a basis. If 0 is in the set, it's not a basis. 0 is linearly dependent. Any set containing 0 is linearly dependent. So that must be the case. Anyway, so if x, yep.
So you said that would always be a subspace of V, but if T was the identity transformation, then how would it contain 0?
Because identity maps 0 to 0.
Okay, so this isn't you plug a particular x into there and generate a...
No, you plug a particular x into there and generate that list. But if you plug 0 into there, the 0 maps to 0. Any linear transformation takes 0 to 0, so...
Okay.
Yeah. No, that's not quite, I'm sorry, you're right. My bad. I'm missing a very important 4-letter word right here. I know it's liberty, but we're allowed this one. Let's see here, so span. Okay. Yeah, thank you. Very good. You're justifiably confused. Thank you, thank you. Okay, so I think everything else I wrote is okay though, but missing a span right there. Because this is not the set. This is this is the basis for W. So the argument goes something like this. You know, first of all, if you look at the set just containing X, this is linearly independent, right? And if that's linearly independent, then we can say, you know, let, you know, K, well not K, let's say let, you know, let N, whatever, M be largest integer for which X, T of X, T M minus 1 of X is linearly independent. And then basically he proves that, so this is on page 3, let's see, where I was at, 314, I think. Let's see here. He says, let J be the, so he uses J instead of N, let J be the largest positive integer for which this is linearly independent. He calls it beta. He said, now why why must such a, let me call this thing beta here like he does. Why does such an M have to exist? We're assuming what? The dimension of V is less than infinity, right? So such M in the natural numbers must exist, right? Otherwise what? Otherwise you'd have a set with more than the dimension of V linearly independent vectors, which is of course absurd, right? So there must be some M like that. And then what the book does is he says, well, he says Z is equal to the span of beta, all right? He says Z is equal to the span of beta. And then he gives arguments which prove that in fact Z has to actually be the full T-cyclic subspace generated by X. But, so one thing it's just kind of, I found it very unsettling when I've run across this argument at various points. It's like, wait a minute, how do you know this is linearly independent? Well, if this is linearly independent, and at some point it has to not be linearly independent, there has to be a largest M for which that's linearly independent. And it turns out that you can argue, if you look at the book on page 314, that in fact not only is the span of this beta a subspace, it's a T-invariant subspace. And in fact, this has to be equal to this right here. Right? And since you know that this is equal, you know, this is dimension K, right? Since we're given that this is dimension K, then how many vectors are here? There have to be K vectors there, right? So that implies basically that, you know, M minus 1 has to be equal to K minus 1, right? My bad. Let me be less weird. Let's just say M equals to K, right? I mean, that's the point. Sorry, I don't know why I wrote what I wrote. I mean, it's not wrong, it's just stupid, you know? So, I mean, you're just done with the quiz. You might have the same feeling. I don't know, but I know I usually do. But anyway, so the point is that's the basis, all right? So you can generate the basis for a T-cyclic subspace simply by powers, you know, by a vector and then operator and operate again and again and again. This generates the basis. That's actually kind of neat. So if we, you know, suppose that we look at the matrix of T restricted to W here, with the base, you know, this basis, this beta basis, then we'd be looking at, like, you know, x, t of x, right? And then finally, you know, t, okay, so we get all the way up to the k minus 1. I'm sorry, there's something off in my...
Isn't that, if it's dimension k, shouldn't it be that n minus 1 equals k, or am I reading that wrong?
Well, I know that the last column's interesting is the thing that's bugging me. Oh, I'm an idiot. Like I said. What am I missing? How do you calculate the matrix of a transformation? Is it just the basis? Do you just put the basis and look at the coordinates of the basis? No, that's dumb. What has to happen? Good grief. T, right? T of x. T of that. T of this. We look at the coordinates of t acting on the basis. That's the matrix, right? Duh. Good night. All right. Anyway, so the point is that the first bunch of columns are really easy. You know, you have just 1, 0, and then you have 0, 1, and these are all zeros. And this goes on, right? Until finally you get 1 in the next to last column, right? And then what happens in that last, this column right here? See, look at this. So why does, this is also really, you know, parts of this theorem seem very mysterious, but they're actually kind of like almost immediately logically necessary. This right here, why is this true? Well, if k minus 1, you know, x, t of x, all the way up through t to the k minus 1 of x are linearly independent, that means that if I look at more, it has to be linearly dependent. And since it's linearly dependent, there must exist a polynomial, right, defined by these coefficients, which gives us 0. And you can argue that the coefficient of the leading power has to be, you can make it 1. All right? You can think through that. And if that, yeah.
With that matrix, wouldn't it be...
We're not done yet. Yeah. So the next thing, I think I know your answer. So we solve for this. That you can finish your question. Maybe it's the same thing I'm about to do.
Wouldn't the leftmost one be 0, 1, 0, 0, 0, 0, 0, and the next one be 0, 0?
Oh, yeah. Oh, that's an even better question. That's not a question. That's a comment. Oops. I will take it. I accept your correction. Thank you. Yeah. So, yeah, like that. Which I think puts the 1 here, right? Yeah. So you have 1's on the subdiagonal. 1's on the subdiagonal. And then the last column, notice that this gives us like t k of x equals to like minus a0x minus a1 t of x, you know, minus a k minus 1 t k minus 1 of x. You guys see that? So this equation that I'm about to underline in orange, this tells you what the coordinates are for t acting on the last basis element, right? See, because that puts a minus a0 here, and then next up minus a1, and so forth and so on, all the way down, until finally a k minus 1. All right? So that's the matrix with respect to the T-cyclic basis. And then this comment that the characteristic polynomial is what it is far less mysterious, because if you calculate the characteristic polynomial of this matrix, it's as simple, but not too hard not too hard a calculation to show that the characteristic polynomial of this matrix is that. All right. So I'm not going to do it, but you can work that out. So there's a little bit more of the proof of this theorem, which I'm not going to prove the entirety of, but I've done a lot of it at this point. So, oh, lest I forget, is let us attendance. So moving on here, guys. Well, I'm not really moving on because the truth is this is right under the surface if we start looking for it, all right? So I'm going to try to circle back to this and show you what I mean by that as we go on. But now I am in my section 5.4. It's section 5.4 of my notes, but it's really chapter 7 in the text in Insel, Spence, and Friedberg, right? So chapter 7. So we're going to come back to chapter 6 in the last story arc of this course, but we're in chapter 7 basically here. And so I'm just going to dive right into it. The basic definition that we need is this: a generalized eigenspace with eigenvalue lambda for t, a linear transformation from v to v as usual. Is denoted k sub lambda. Now here, lambda is in the field, right? Lambda is in the field of the vector space, to be clear. So we're going to denote it k lambda. And we say x is an element of k lambda if there exists whatever, m in the positive integers for which t minus lambda to the m power acting on x equals 0. So that's the definition. So the generalized eigenspace, it's going to do what? Now, it's important that it has an eigenvalue, all right? So this lambda is not just any old number. It has to be a root of the characteristic polynomial. We're assuming that the linear transformation actually has a characteristic polynomial which has zeros in the field, right? But this is the generalized eigenspace, and vectors in here are called generalized eigenvectors, all right? Let me give you a slightly more nuanced thing. This is, I don't think in my notes at the moment, but this is something I always tell students, so I'll tell you guys. Definition, if t minus lambda to the p minus 1 power acting on x is not equal to 0, yet t minus lambda to the p power acting on x is equal to 0, then x is generalized eigenvector order p with eigenvalue lambda. It turns out those are really interesting because of their connection with this T-cyclic stuff, as it happens. But that's a longer story I probably won't do justice to today. But I'm going to try to at least get us started on it today with what time we have. Now, so this is generalized eigenspace. And so the fundamental thing is the following theorem we can state about it. T t, v to v, dimension of v less than infinity, everything's all finite dimensional here, guys. So linear transformation. Lambda and eigenvalue. Oh man. Then here's a couple items for us. First of all, k lambda is T invariant subspace. All right. And we can say a little bit more. What do you guys think about E lambda? How would that figure into the story here? What was E lambda? Remember? E lambda was equal to the kernel of T minus lambda, right? It's just eigenspace. So that is going to be a subspace of the generalized eigenspace. So eigenvectors are special cases of generalized eigenvectors. In fact, if you look at my other definition, every eigenvector is a generalized eigenvector of order 1. B for distinct eigenvalues, mu and nu, well, lambda and mu, I guess. What do I got here? Mu and lambda. We have that k lambda intersect with k mu is what? Empty set. Right spirit, wrong set. Yeah, the zero set, right? Because it's the intersection of two subspaces. So 0 has to be in there. But in fact, it's all that's there. Right? So now if you wanted to be like span, I can meet you there. Right? So span to the empty set. There you go. If you want to bring that back into it. And then here, for any scalar, C, any scalar mu not equal to lambda, the restriction of T minus mu I to k lambda is 1 to 1 and onto. So the proof of this is given on pages 478 to 479 of the textbook. And the proof of part B is particularly interesting. I'll probably talk more about it some other day. It involves polynomial algebra in a kind of an interesting way. Now, the next theorem, I'm going to skip that one. Let's see here, that one, skip that one. All right, so theorem 5.4.5 in my notes, which is, let me just give you the corresponding theorem in the book. So what I'm trying to do right now, guys, is just tell you the theorems which are like the takeaway message of chapter 7. And I'm not giving you all of the theorems which kind of build up the results. So like in my notes, there's a couple theorems there which are kind of like intermediaries. They're like a step on the, they're partly to where we want to get to, but they're not where we want to be. Let's see here. This one's important though. This is, I believe, 7.4 in the text on page 480. And here we have if T, is a linear transformation on V with characteristic polynomial P equal to, let's say, T minus lambda 1 to the M1 power, T minus lambda 2 to the M2 power, T minus lambda K to the MK power, all right? So this is the context. We're looking at a linear transformation with a characteristic polynomial that completely factors over the given field, all right? So it's said to split. Splits over F, okay? Then for I equals to 1, 2 all the way out to K, let beta sub I be basis for K lambda sub I, all right? Then here's the deal. A beta I intersect beta j. Now here's your empty set. There you go, right there. For I not equal to j. Obviously, if I is equal to j, it's kind of silly. And then B beta, which is the union of beta 1 through all the way through beta k, is ordered basis for V itself. And then C, the dimension of the generalized eigenspace is equal to the algebraic multiplicity of the root for all I. So this theorem does what eigenspaces couldn't do for us. They give us space which completely give us a, what is this, I guess this isn't stated here, but, well, let me forget about the book for now. So this takes like 3-4 pages of careful arguments, some of which are quite delicate to like establish all of this, all right? Like it's not easy. But what does it mean if we have this theorem? It means that the generalized eigenspaces are what? They're, just like we proved last class, they're independent. See, because we have that the union of their bases is a basis for the whole space, right? That was one of our equivalent lists of independent subspaces, right? So in view of this theorem, a corollary to this theorem is that in this context, we have that V is the direct sum of the generalized eigenspaces. So, right? And not just this, as I was saying in the previous theorem, these are T invariant subspaces, right? Right? They're T invariant subspaces. So what does that make the matrix of T look like? If I was to look at the matrix of T with respect to such a basis, what would it look like? Exactly, block diagonal, right? So T beta beta would be the direct sum of like T, T sub k lambda 1, beta 1. I really regret my insistence on writing beta beta at this point. It exacts a heavy toll here, doesn't it? The book is so much smarter, isn't it? That was beta 1. Beta 2, beta 2. T sub k, kk? K lambda k. Oh, phew, that was close. Beta sub k, comma, beta sub k. Can't ever be too careful these days. So yes, if we had such a basis, we would have a direct sum decomposition for our operator, like this, which is super nice. So then the question then becomes, okay, so this theorem, these theorems are true. This is the deal. These are what generalized eigenspaces look like for us. So how do we actually find these bases and put them together, right? That's kind of the natural next question to ask. So I want to show you some examples of this actually in action. And of course, I'm talking about for linear transformations, but we could just as well talk about for a matrix, right? So let me show you an example. One of these guys here. So, I mean, the truth is, like, the full algorithm to describe how to calculate this basis beta, this basis is called a Jordan basis. Provided that you arrange the basis in such a way that the vectors are in what are called chains of generalized eigenvectors. So, like definition, if you have T minus lambda, let's say Vj equals to Vj minus 1 for j equals to 1, 2, all the way out to k, and we're defining v sub 0 to be 0, then v1, v2, dot, 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 vk is a k-chain with eigenvalue lambda. And you can prove that these vectors are linearly independent. That's a good exercise to prove linear independence of a k-chain. But in any event, notice how this works. So I'll write it out explicitly. We have t minus lambda v1 is equal to 0. We've got t minus lambda v2 is equal to v1. T minus lambda v3 is equal to v2. So if you look at this, this says what? T minus lambda acting on it twice on v2 gives us what? Equals 0, right? Because that's t minus lambda acting on v1, which is 0, so that's 0. And this, on the other hand, tells me that t minus lambda squared acting on v3 is equal to, well, v1 apparently. So that then tells me that t minus lambda cubed acting on v3 is equal to 0. So and this continues until we get to the last one. And after a little bit of calculation, or perhaps an induction proof, if that's what floats your boat, we get the k minus 1 acting on vk is v1, and t minus lambda to the k power acting on vk is equal to 0. So what does this all mean? This means that v1 is an eigenvector, v2 is a generalized eigenvector of order 2, v3 is a generalized eigenvector of order 3, vk is a generalized eigenvector of order k. And I can arrange these basically into a T-cyclic basis. I can use that T-cyclic idea if I wanted to. I'm not sure I want to here. But maybe I should. Let's see here. So how can we, if I've got time, maybe, debatable. Let's see here. How do I get how can I rewrite, if I call this thing beta, I can rewrite this as what? This is vk, and then what? T minus lambda vk, right? Because that's vk minus 1. And then I've got t minus lambda squared vk, because that's v, vk minus 1. And this goes on until finally I get to tk minus 1. My bad. T minus lambda to the k minus 1 acting on vk, right? And that, by construction, is v1, right? So it's that same idea we had at the start of lecture, right? It's this T-cyclic basis, and as such, it's interesting to look at what the matrix of T looks like with respect to this base. Now, my bad. See, because is this? I mean, this is illegitimate. Why? Right, I've anti-ordered it, right? So it's like this is bizarro beta, These are all topsy-turvy. So, and I do like the ordering here, because if I look at then the matrix of T, let's suppose that V is just equal to the span of beta. So this is all there is. All right, this is all there is. If this is all there is, what's the matrix of T look like? Well, the matrix of T with respect to this beta basis, not the bizarro, which is the bizarro is natural for the T-cyclic identification, but understand it's out of order. So we got the matrix of T with respect to V1, right? Matrix of T with respect to V2. Finally, matrix of T acting on Vk, right? And what is that? Well, that is lambda V1. And then you've got lambda V2 plus V1. And so forth and so on until finally we get to lambda Vk plus Vk minus 1. Beta coordinate of that, which I'll write out here. So what you're looking at is lambda, 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 all down the diagonals. And starting at the second column, I've got a 1 right above it. So I got a 1 here. If I was to write the next one, I would get 0, 1 lambda there, all right? And this continues. Lambda's down the diagonal, and 1's on the super diagonal. So if I was to write the next one here, well, anyway, you get the idea, I hope. 0's everywhere else. In other words, I could write this as lambda times the k by k identity plus n sub k, where n sub k is this thing. That nilpotent matrix of order k that I've had you guys work problems about, I think, somewhere. So the form of the matrix is lambda times identity plus this super diagonal piece. This has a name. This is the Jordan form. So the Jordan form of order k with respect to lambda is literally equal to lambda times ik plus this nilpotent matrix of order k. That's the k by k Jordan block. And what we're going to see next time is that we can pick chains out. I'm not going to prove it really, but I'm going to describe it at least. We can actually find enough chains of generalized eigenvectors that we can put those chains together in a basis. And with respect to that basis, the matrix of the transformation is simply the direct sum of these Jordan blocks like this. And that's as good as we can get. Like, that's the generalization of diagonalization, is the Jordan form of the matrix. And we can calculate all kinds of things with the Jordan form. It's quite amazing. It answers the question of when is it given two matrices, are they similar? Well, the simple way to check on that is to calculate the Jordan form of both and see if they're the same up to reordering. If they are, well, then the matrices are similar. If they're not, well, they're not. Anyway, I got more to say, but that's it for today.